There you are. random element in the bag is chosen, and that's what gets removed in the string. Okay? And random has a very specific meaning here. It means that among all of the things that are currently in the random queue, one of them gets chosen, each one is equally likely to be chosen. So random is not the same thing as arbitrary or convenient. It really means each one is equally likely to be chosen. So if you do the same set of operations more than once with the random cube, like you add a bunch of stuff, maybe the numbers 1 through n, and then you remove n times, well, the first time you do it, you'll probably get a different ordering of the elements coming out than the second time you do it. In fact, if you want a random permutation of 1 through n, put them all in there, and then remove them all, you'll get a uniformly random permutation. So that's what a random queue is supposed to do. And currently, the implementation does that. And the way it does it is it puts the elements in an array list. So when you add, it just appends it to the end of the list. That's fast, right? Adding something to the end of an array list, that only takes constant time. And when you remove, well, it takes a random index I between 0 and the number of elements minus 1, and then removes that ith element from the array list. Okay, so this indeed does give you a random element, right? From all the stuff that's in there, we take a random index, and so we get a random element. What's the problem with this implementation? Yeah. Yeah. So the remove operation takes a random element, and so it's equally likely to be at the end, at the front, or in the middle, or anywhere else. So somehow, on average, you're removing from the middle. And you can formalize that by saying, on average, the expected value of the index that you pick is about n over 2, which means, well, on average, you have to shift n over 2 elements once you do this remove. So shift n over 2 elements. So the question says, fix this. Make it so that it's still random, but the remove operation goes a lot faster. I can't tell you anything more about that without answering the question. I think there's maybe a hint, or I'll give it to you now. The answer is basically 1 or 2 lines of code to answer this thing. Make it work fast. All right. The second question, let me see it up there, is to implement something called a bulk array deck, which is just another kind of array deck. So remember, this array deck class is this thing that stores lists in an array. The list starts at position j in the array and continues at positions j plus 1, j plus 2, and so on, so that it even wraps around the end of the array and goes all the way up to position j plus n minus 1, modulo length of the array. So that's this array deck class. And now I want you to implement a method called add all. It says, starting at position I in the list, add all the elements in some collection C. So C is another collection. It could be a list, it could be a set, it could be anything. Like C, you can use for loops to iterate over the elements in C. And add those at position I. So if we view it abstractly, we have a list. And here, position I, put all the elements of this other collection C, stuff them into the list starting here, so make the list grow out of that. So currently, there's a default implementation of this. The way the collection framework works is there's these things called abstract lists and I think abstract linked lists or something, but there is already an implementation of this. And the way that that implementation works, it's just inherited from this abstract class, is it just repeatedly inserts the elements of C into this thing. So it inserts the first element of C into position I, and the second element in position I plus 1, and the third element in position I plus 2, and so on. If you think about that for a while, that's not going to be terribly efficient. So what's the problem with that solution? It's array-based list. When we add one thing, we have to take all these elements and shift them over one position to make room for the thing that we're adding. And so now, that's not so, that's fine if you're adding one element, it's sort of necessary. But now, if you're adding many elements, well, you take all these elements and you shift them over one position to make room for the first element, and then you take all these elements and you shift them over one position again to make room for the second element, and then you do it again for the third element. So somehow that seems kind of stupid, right? All these elements are being shifted repeatedly, when what you could have done is just shifted them enough to make enough room for everything in one go. So implement that, basically. So make it fast that way. And of course, there's some specific runtimes required, so that if you're adding near the front or near the back, it should be fast. In the middle, it'll still be kind of slow, but it'll never be as bad as just adding the elements one at a time. So make that work efficiently. Questions about that? Fairly easy. So now, a couple of more manipulating arrays. One of them I mentioned in class. I gave you a lot of tips on how to do this. So this is part 3. Okay, part 3 is a little bit different. In part 3, the idea is to implement an array deck and avoid this operation, this mod operation. So I told you in Java it's not such a big deal because everything else is so slow in Java that the mod operation doesn't amount for much. But in other programming languages, this mod operation can be the thing that makes it quite a bit slower. So you want to look at techniques for avoiding it. So you want to be able to do sort of these circular arrays or these arrays that have 2 ends on them without having to do this. And question 3 asks you to implement this in the following way. By not using a circular array, but by wrapping around, or by avoiding this wrapping around issue. So looks similar. The data starts at position J. And goes to position J plus n minus 1. And it's simply not allowed to run off the ends. So it's not allowed to, you're not allowed to add things at the end and have it wrap around. Instead, if you find yourself in a situation where you've added stuff, and now you're going to add something which would normally cause the data to wrap around, you do a different kind of operation, which is to resize the array so that its size is 2 times n. and take all the data and put it in this new array, starting at position n over 4 means, starting at position n over 2 and going up to position 3 n over 2, putting the data here in the middle. So this is you don't just resize when the thing gets completely full. Actually, the more common thing, or the different version of that, is you resize anytime you run off from the end. Either because you add stuff at the end and you ran off this end, or you add stuff at the front and you ran off the front of the array. Then it's time to make a whole new array, take all the data, and copy it into the middle. Okay. So implement that. And also, you're not asked to do this for the assignment, but again, think about why this would be efficient. It's another one of these major restructuring operations where we copy one add operation, ends up copying all the data in the array, and then think about, well, why should that be, why isn't that too expensive? Why isn't that going to add up to too much? And when thinking about that is, well, once you do this, how long is it going to take you before you end up in this situation again? Sort of the reason for designing it this way is by sticking the data in the middle, it's not near either of the two ends, so you won't end up in this situation for quite a while again. Yeah. Yes, you could also do the resizing to make it smaller, but that just means you write one resize method that does the right thing, and you call it at the appropriate places. Good. All right. Question 4. Again, is about avoiding this mod operation, but it's about avoiding it through using this bit trick that I showed you, where you replace something mod a.length. You replace that with x and something like 1 d. Where a is 1, where a dot length is equal to 2. So same thing again. Now you're allowed to, the stuff that the data is allowed to wrap around, but when you do these calculations, they're not modulo a dot length. You simulate doing this modulo a dot length by using this bitwise. And of course, to make this fast, this thing here you store in mass. So you're not just doing it every single time, and you're just ending it with whatever index you're using. The one thing I'll tell you for free is it's not just a matter of going and taking the array deck and replacing all occurrences with mod a.length with this. Why not? Yep. Yeah. In the current implementation of array-deck, a.length is not always a power of 2, and this formula that we covered only works when the length of a is the power of 2. So that's an issue, and so somehow you need to fix up the whole resizing procedure so that you always get something that's a power. And while doing that, make sure you don't make it too efficient as well. So that's the issue. Okay. Question there? All sounds very easy, right? And then the last one, which is the one that probably the hardest of the bunch, is to take this root array stack we discussed last class. And remember, this root array stack has this great property of not using too much extra memory. So remember, that's this thing that stores a list in a sequence of blocks, where the blocks have size, the blocks are arrays. The blocks have size 1, 2, 3, 4, 5, all the way up to some size R. And there's a list that stores the pointers to these blocks. There's some table here, some blocks, and that's a list that stores pointers to the arrays like 1, 2, 3, 4, 5, and so on. So this is nice because it doesn't waste too much memory. But not only that, if you push it a little bit harder, you can actually make this thing faster than any of the other lists. In particular, you can make it faster for doing add operations that are close to the middle of the list. So why is that? Well, what happens when you add, let's say, either near the beginning or near the middle of the list is, let's say 0, 1, 2, 3, 4. Let's say I want to add at position 4, I want to add the value x. Well, currently, what happens is, well, that means you take the thing that's at position 4 and move it to position 5. You take the thing that's at position 5 and move it to position 6, 6 to 7, 7 to 8, 8 to 9, 9 to 10, and so on, and all the way up to n minus 1 to position n. Of course, you do this backwards, it's easier to do it that way. So you end up moving n minus I values. Okay. So that's expensive. That takes order n minus I time. But if you look at actually what's happening here, is you're really, in this array, you're putting in one value right here, and you're kicking something off the end, kicking the last value out. So the last value of this array is kicked out. And where does it go? It becomes the first value in this array, which means that the last value in this array gets kicked out and becomes the first value in this array, which goes on this whole way until you get to the final array where all you're doing is now adding the first value to this final array, and maybe if that makes it too big, you kick it out into a full fresh array, or maybe not, maybe it stops there. So there's a better way to do that. Right? So what's this operation that we keep doing on this array? The most common operation we keep doing is we add something here, right? It came from the previous one, it goes on the front, and we remove something here. That's really what keeps happening in all these middle arrays. Now, if these things are just implemented as straight arrays, well, the way we do that is by shifting everything over one position and the guy at the end falls off. But if we think about what kind of data structure could do this in a more efficient way, well, this is the kind of thing that a deck can do. Right? We can add at the end of the deck and we can remove at the other end. So these things here, instead of just having them be plain old arrays, use decks here. all of these things become checked. Which means that you can add and remove at the front or the back in constant time. So this n minus I values that you use to shift, well, now you end up shifting the ones in this block. And now remove is a similar kind of thing. Right? If I want to remove the fourth element, that means I end up taking the first element from this one and moving it here, and then the first element from this one and moving it there, and so on. So the same idea. But that again doesn't require shifting in particular text, it's just removing first and last thing. And so all that shifting, these n minus I values, you can replace with, it ends up being something like square root. Well, at most, the square root of n deck operation. Okay, so square root n deck operations, each of which take constant time, will, if I is small, is going to be much smaller than n minus I. And it's really not exactly square root n deck operations, it's at most square root n, it's at most the number of these blocks. But if you're deleting near the end here, the black block, well, you don't do any of those deck operations, so they're more or less free. In fact, if you're deleting near the end, the typical thing that happens is you're only doing regular old operations in the last block, and the last block only has size also square root n. So if you analyze this carefully, what you'll find is it doesn't matter where you add or remove, it never costs you more than square root n. In fact, it ends up being the minimum of square root n and n minus I. So this British array stack idea not only gets you space saving, but actually if what you want is some kind of random access to be able to add and remove anywhere, then that ends up being a lot faster than just using an array list or even an array list. Remember, the way to think of this is when n is 1,000,000, square root n is only 1,000. So if I wanted to add into one of these British array stacks or even an array list that had 1,000,000 elements, and I want to put something at the front, then I have to move 1,000,000 elements. If once you've implemented this thing properly, well, that instead of moving 1,000,000 elements, you'll only do 1,000 deck operations. So you're looking at a speed up of a factor of roughly 1,000. So well worth doing. So that's what you have to do for this assignment. And then there are the testing portion of the assignment. Which is basically writing tests for all of these data structures that you've done. And what I'll tell you about these tests, describe what should happen. Again, the TAs are going to submit faulty implementations. These are implementations that are either incorrect or they're too slow. And your job is to write tests that expose this. So what your tests should do, they return true or false. And if they receive a good implementation, one that works, then all they have to do is return true. So they run their tests, they say all tests passed, and they return true. If they receive an implementation that's no good, that is either too slow or that is incorrect, well, three things can happen, any of which is all right. If the data structure is really bad, the test will just crash. We'll throw an exception, that's fine. That means you discovered an error in the data structure. If the test is really, if the data structure is implemented in a way that has poor performance, it may just take a really long time for your test to execute. The server doesn't like that, so it will just kill your test. So that counts as discovering the error. Or maybe the data structure didn't crash. Maybe it also didn't take a long time to execute, but your test knows what values it put in, and it knows what values came out, and it realizes that one of the values that came out was not the right values. Like, you put X at position 0 in the list, and then when you tried to read position 0, some other number came out. Then your test should return false. Your test failed. So, in the case of failure, 3 things are acceptable. In the case of success, the only thing you can do is return. Good, so that you have to write tests for one of these bulk array decks. You have to write tests for basically an array deck that works for both questions 3 and 4, and then one for this British array stack as well. So one nice thing is 4 of those essentially implement the list interface, and so they can all use sort of the same correctness test. They just maybe have different performance characteristics. So you can feel free to reuse parts of your testing that way. The one that's a little bit tricky is the random queue, because you're supposed to put things in and they're supposed to come out in random order, but how do you know if something is in random order? So try and come up with some reasonable tests for that. And there will always be some chance that your test may say that there's an error when there's actually not, because there's always some probability of really strange behavior from a random queue, because anything can happen. Like, you could put in the numbers 1 through n, and when you remove them, they come out in the order 1 through n. That's one of the possible orders. If your test saw that, it might think, hey, this really doesn't look random to me. Maybe you should try it again or something. But there, don't worry. You should be able to make tests which have an exceedingly high chance of success if the thing is really random, and you may not detect things which are only pseudo-random, but as long as the stuff is fairly random, it should get through here. So we're not going to try and figure too much there, but for example, things should fail if the elements always come out in the same order they were put in. That would definitely be something to test should fail. Easier than that is simply if you do the same operations repeatedly and the elements always come out in the same order. So you put 10 elements in and you take 10 elements out. Do that twice. If those 2 orders are the same, there's a good chance something's really wrong. Because there's only a chance of 1 out of 10 factorial that should happen, and 10 factorial is a huge number. So you should probably fail that kind of. All right. Any questions? No? All clear? So one thing that I'll warn you about is that this assignment number 2 in this course, is typically the killer. It's the one that people do the worst on. The reason is these data structures are surprisingly finicky to implement for us. All it takes is one little off by 1 error, one little counting error. You get one single index wrong, and the whole data structure is incorrect. It's crashing all the time, and it can be quite hard to debug. So you have a lot of time to do this assignment. I suggest that you make use of that time. Don't wait until the last minute. The bugs in data structure implementation can be very difficult to hunt down. This is true both for array-based data structures, which is what this assignment is about, and you'll see that it gets even worse when you start considering pointer-based data structures, which is basically the next topic. So don't dilly-dally. Start this assignment as soon as possible. another good reason for doing that is just that, well, this assignment covers material that we've covered in the last 2 weeks. This is the time you'll understand it the best. If you come back to this in 2 weeks from now and then start working, you'll sort of have to relearn. Now is your chance to solidify your understanding. All right. So, for whatever reason, my laptop doesn't like the projector in here, so we're going to do something awful and actually record from a screen. So I know at least a couple of people have looked at the videos. I don't recommend skipping class and just watching the videos, but they maybe can be helpful. Okay. Okay, so I promised you a review, and I know, even though you don't necessarily speak up, you can tell by looking at some of your faces when we're doing amortized analysis, things look confused. Some of you look confused, some of you look like you wanted to understand this, but didn't quite. So we'll very quickly review a couple of amortized analyses that we've done, just so maybe you get the big picture again. So remember, this was to attack questions like, how fast is this method for an array stack? Same thing as an array list in Java. And we said, well, if we ignore the first line, then it runs in constant time. So all we're doing is adding at the end, and that's just incrementing an integer and setting a value in an array. But there's that first line that's the issue. And then we ask more complicated things. Well, what if you add into the middle of the array or position I? Well, we figured that out. We have to move n minus I elements. Make room for x and then put x in there. So if we ignore that first line, which is the one that does the resizing, then then we can tell you how long it takes to run this thing. And amortized analysis is about accounting for not having to, the fact that we ignore that first line, making up for it later by saying something about the cost of those operations in that first line. And so you get these theorems that look like this that say, an array stack implementation. If we ignore the cost of resizing, all the calls to resize, then get x and set x take this amount of time, and add and remove take this other amount of time. And then you always put on an extra clause at the end of this theorem that says, oh, and by the way, if we start with something in an empty data structure, and we start adding and removing from it this way, then all the time spent during calls to resize, we can tell you what that is. We can upper bound that. And in this case, the time spent resizing is just proportional to the number of add and remove operations. And we think of this as a sort of amortized accounting because we're saying, yes, there are times when things are expensive, but in the end, it works out to only being proportional to the cost of all the add and remove operations. So if we amortize it over the add and remove operations all the time, where if you work, then you maybe get paid once a month. You get a paycheck. I don't know how much it is. Maybe a few $1,000s. And well, you'd like to know, for instance, how much money do do I get paid for every day that I work? Well, you count how many days you work in a month, you look at that some number M, and you look at how much money you get paid at the end of the month. You take that amount of money and divide by M, that tells you how much you get paid for each day. Even though you're not really getting paid at the end of every day, but you can figure it out that way, and you can even go down to figuring out your hourly wage. Even though, of course, it's not giving you money every hour for doing this, but we still think of this as, how much am I making per hour? We do these kinds of calculations all the time. And so this is saying, well, how much resizing are we doing per operation, per add and remove operation? Okay, well, some cost. Okay, so how do you prove a statement like this? Well, resize copies n elements from the current array into a new array whose size is exactly 2 times n. And it's going to take quite a while, so this is a picture up there with the 3 dots in an array of size 6. That's one of these half-full arrays. It's just been resized. And it's going to take a long time before it becomes full again. It's going to take at least n add or remove operations. And then we'll have to copy these 2 n elements. So by now, if n is the number that were there after the first resize, by the time it becomes full again, there's now 2 n elements, and we're going to copy them. So that's what happens if the thing becomes full. On the other hand, we may also resize if the thing becomes too empty. And if it becomes too empty, that's because we deleted, if n is the number of elements originally there, well, we deleted a third of them, and then we'll have to copy 2n over 3 of them. Is that clear? So in either case, these are the 2 cases. Then we had this array that was half full after resizing. Now it's either completely full or now it's only 1/3 full. The number of elements that we're about to copy is only twice the number of add or remove operations that happen in the mean. So either we're going to copy 2n over 3 elements, but we've done n over 3 remove operations, or we're going to copy 2n elements, but we've done n add operations. And then that does. That says, well, if we do m add or remove operations, then at most we do 2m elements that get copied in full by adding and And if you look at the resize method, really the only work that it does is copying stuff. Everything else is related to that. So the amount of work done is proportional to the number of elements copied. So that's order n work overall. And that's how we get these final clauses at the end of these theorems that say, that tell us the total amount of time we spent. Would anybody like to ask me anything about this now? This is your last chance. There will be questions like this on exams, for example. Okay. It's not true that it's your last chance. You can ask me questions about it. We also did a similar analysis on a dual array deck. And again, it always basically boils down to looking at what the picture looks like the last time we did a rebalance, right after we did the rebalance, versus what it looks like the next time before we do a rebalance. And in this case, when we rebalance, or when we rebalance this thing, we have the front stack, we have the back stack, and they both have the same size. Yep. This is the thing we call the potential. The difference in size is the thing that we've been calling the potential. And there's a little bit of cheating here because it's not always exactly 0. Sometimes it's 1 because the number of elements is off. So that doesn't add up to anything. And then we don't rebalance until one got to be 3 times as big as the other. So that means that the difference in size now is at least half the number of elements, right? One of them has at least 3n/4 elements, which means the other one has at most n/4 elements. The difference between 3n/4 and n/4 is n/2. So we're about to rebuild it's because the picture looks like this. We're about to rebalance. That's the situation, which means that in the meantime, we look at the add operations. They can change the difference between the front size and the back size by 1. Right? You add into the larger one, then the difference increases. Remove operations, similarly, if you remove from the smaller ones, then the difference also increases by 1. Sometimes you get lucky and you add or remove into the right place, and then the difference actually decreases. That's not so important. So finally, we get the same kind of result. So if we're going to do a rebalance and we're about to copy m sub I elements, then the total number of add and remove operations in the last time we rebalance is at least m sub I/2. And so we finish the same way. The total number of elements copied by all the calls to rebalance is at most twice the number of these add and remove operations. I'm not sure why there's a 4 in this last sentence, but m add or remove operations should result in at most 2m elements copied by rebalance. That's the typo. But the important thing is that the total work done by these things is proportional to m. And again, we get one of these theorems that says, well, when you do this, here's the running times if you don't account for rebalancing and resizing. But if you do account for it, then that adds up to an additional total of m work, or if you like, average of the function amount of work per add and remove operation. Okay, this one we sort of glossed over last time. The British array stack, we said there's this sequence of blocks of size 1, 2, 3, 4, 5 up to B, and all of the early blocks are full. So the first block is full, the second one is full, the third one is full. The last one is maybe not full, and in fact, maybe even the last one is maybe completely empty, and the second last one maybe is only partially full. So the question, I guess, is, well, why allow a block that is completely empty to be able to stick around? The whole thing was to save, the whole point was to save space with this thing. So why allow for one block at the end which might be completely empty? What could be the possible reason for that? So I'm saying that there are times when the data structure, the British array stack, looks like this. Block of size b minus 1. full, and maybe this one is completely empty. So if that happens, it could happen because maybe there was some stuff in this block and then we removed it. Now there's nothing there. So why not get rid of this block right away as soon as it becomes empty? Yeah, because we want to avoid a situation where we end up with this. So we fill up this block of size B minus 1. We add one more element. That means we need a block of size B to hold that element, which is fine. We allocate that thing. But now if the next operation is to remove this element, then what are we going to do? Delete this block. Okay. And then we add one more element, and then we have to create this whole block again. And remember, this is not a small block. This is a block whose size is about the square root of 2 times n. And so if we kept adding and removing like this, just so that you get one element in this block and then take it away, and another one and take it away, that means every second operation we do, we're allocating an array of size square root n. And typically that means that the array gets zeroed out. In Java, for example, it means all the values in the array are set to null. And so that's an operation that takes time proportional to square root of 2n. But if we're adding and removing at the end of the list, that's supposed to be an operation that takes constant time. So the trick that we use is simply not to delete this thing. The only time we will delete this thing is if we end up with 2 empty blocks at the end. Then we'll delete one of the empty blocks. To avoid this thrash behavior of adding and removing repeatedly, what we would like is for there to be a long time between adding and removing operations. So let's see if this strategy of allowing for one fully empty block and one partially empty block, if that resolves it. Okay, so if you resize one of these things, meaning that you grow it, it creates a empty block size, and we won't resize again until we fill this new block. So, for example, if we just added this new block, then we won't resize until it gets all filled up with data. Or we empty the previous block. Now, since we just allocated this block, that means this block, the previous block, is full. Otherwise, we didn't need to allocate this. So if we create this block, it means this one is full, and this we're about to add something, but right now it's empty. Create a block of size B. After we've done that, there's basically B minus 1 empty slots in it. And the previous block has B minus 1 values. So if we fill this thing, it's because we did B minus 1 add operations. And if we empty the previous block, that's because we did B minus 1 remove operations. So nothing is going to happen again until we either fill this thing, back to the same thing. Right? How long does it take to create this block? Well, it takes order B time to allocate this array of size B and zero it out. And then we're not going to have to create any other blocks until we either do B add operations or B minus or B remove operations. And so the time between creating this block, or let's say if we just created a block, the time since the last time we created a block, the number of operations that have happened is at least B minus 1. B is the size of the block that we're creating, so that's the time it takes us to create it. So that gives you the same result that there's a little furthermore with these rooted array stacks. There's also an amortized analysis that happens to ignore the cost of resizing, which is this thing that creates a new block in a rotation array stack, then it's easy to calculate the times of getting and adding and removing and setting. And if you count for the cost of resizing, well, you get the same statement. That over a sequence of m operations, starting with an empty rotation array stack, you spend a total of order m time resizing, which means adding or removing. Any questions there? Last chance to ask me a question about advertised analysis. Last thing I want to do is just serve you a reminder go notation. So most of you have seen this before, some of you haven't. But now it's going to start, for the rest of the course, it's going to start to matter sometimes whether or not you really know the definition of this thing, or some things really won't make sense at all. So far we've been playing sort of fast and loose with it, saying, you know, big O of n is something like some constant times n, or at most some constant times n, something like that. But we should make sure we really understand. Well, in general, we shouldn't use language that we don't understand. So first of all, here's a surprising thing. When I write something like big O of g of n, what am I talking about? What kind of object am I talking about? G of n is a function of n. What's big O of g of n? It's a set. Yeah, it's a set. It's actually a set. It's a set of functions. So, I mean, that's crazy. The way we use it, we never think of it that way. But the formal definition of big O of g of n is a set of functions. And it's a set of all functions f of n such that there is a constant c and a constant n0, so that f of n is smaller than c times g of n for all n bigger than or equal to n0. So it's a huge set of functions. In fact, it's an infinite set of functions. That's the formal definition of big O. So notice this set of functions. And when we say something like this is really not correct. When we say f of n equals O of g of n, that makes no sense at all. We're saying a function f of n is equal to a set. That doesn't mean anything. It's not true. It's really ends up being an abusive notation that we use all the time in computer science. Some mathematicians get really frustrated with us because of this. What we're really saying is that the function f of n is a member of the set O of g of n. So we might write something like n squared plus 42n plus 7 equals O of n squared, when really what we mean is that the function defined by f of n equals n squared plus 42n plus 7 is in the set O of n squared. So that's not, I mean, that's an abuse of notation that unfortunately we just have to get used to and get over because it's just, it's so pervasive in computer science. So notice a couple of things here. We have used this equality to really mean membership, and our functions, we often note they don't have names like f and g, and so on. They're just written down as a formula that defines the function. And usually, in most cases, the function, what are the arguments of the function? This value is variable n. So it's some function of n. So we said n squared plus 42n plus 7 is in the set of n squared. So the formal definition says that means that there is a constant c and n0, so that the thing on the left is smaller than c times the thing on the right for all n bigger than n0. And so let's see if that's true. Here's the plot. The red line is, the red curve is 2n squared. The green curve is 2n squared. And the red curve is that function n squared plus 42n plus 7. And notice that at some point, once we get to past 50, the green curve, which is 2n squared, ends up being greater than the red curve. So that says that this function on the left is smaller than or equal to 2 times n squared for all n bigger than or equal to 50. So it satisfies the definition of being in that set, order O of n squared, because it has these two constants, n0 equals 50 and c equals 2, for which it's, yeah.
The way it's written, it doesn't seem like relation is symmetric. For example, when your functions are in O of BPN.
It is not symmetric. That's right. So in general, it's just expressing an inequality. The thing on the left is sort of smaller than the thing on the right. So the big O notation is just it's expressing an upper bound. Okay, so how do you prove this kind of thing? If you did 1805, you would end up doing some examples like this. Well, you say, look at the formula you start with. You're trying to prove that it's smaller than something times n squared. So for n squared plus 42n plus 7. What if I take that 42n and replace it with 42n squared? Do I get something bigger or smaller? Is it always bigger? Is n squared always bigger than n? Depends on n. When does n squared start being bigger than n? Yeah. So we can replace the 42n with 42n squared for n bigger than or equal to 1. And we only get something that's not small. And similarly, 7, we can replace with 7n squared, and that's going to give us something that's not smaller either. But again, that's only true if n is bigger than or equal to 1. If n is smaller than 1, then 7 times n is smaller than 7. 7 times n squared is even smaller than that. So this gives us n squared plus 42n squared plus 7n squared. Well, that's equal to 50n squared. And so what we have is on the left, the formula we wanted, n squared plus 42n plus 7, is less than or equal to 50n squared for n bigger than or equal to 1. And that's the kind of thing that satisfies the definition of big O notation. This constant c is 50, and the constant n0 is 1. That function on the left is in the set order n squared. Okay. Here's another one. 5n log n plus 8n minus 200 is O of n log n. How would you prove that? So we always start with the thing on the left, and we want a sequence of inequalities that say it's smaller than this next thing, which next thing, which is smaller than this next thing. So I usually want the formula to be getting simpler and simpler, having more terms that are you can just add up easily. So what's something that's easy to get rid of than the thing on the left? Yeah. Minus 200. If I don't subtract 200, then I'll get something bigger for sure. Let's see if that's the way it's done here. So the first thing we do is drop the minus 200 and say, well, that's certainly less than 5n log n plus 8n. And that 8n and that n log n, somehow they're incomparable, so I'd like them all to be n log n. And so, well, what if I just switch that 8n for an 8n log n? Well, that's valid as long as n is bigger than or equal to 2. Because if n is bigger than or equal to 2, then log n is bigger than or equal to 1. And so, n log n is going to be then bigger than or equal to n. And now again, everything adds up nicely. We get 13. So that whole thing is equal to 13 n log n. So the thing on the left is less than or equal to 13 n log n, as long as n is bigger than as long as n is bigger than or equal to 2. So it satisfies this condition needed for this for belonging in the set O of n log n with the constant c equals 13 and n0 equals 2. And of course, this is a really sort of easy thing to do. There's a lot of options here, right? You can make c as big as you want and n0 as big as you want, whatever is most convenient for you. Yeah, because log base 2 of n is bigger than or equal to 1, or n is bigger than or equal to 2. And for n less than 2, it's smaller than 1. So that would not be valid. We would now instead be replacing n, right? So we replace n with n log n. And so we need this log n to be bigger than or equal to 1, or else it's simply not true that this one is smaller than that. And you know, these things can get really complicated, but basically they all have, when you try and prove them directly this way, they all have this form that you start with the thing on the left, you keep saying it's smaller than something, and occasionally you end up with these conditions on the right that say, oh, by the way, this statement is only true if n is bigger than 2, this time it's only true if n is bigger than 50, so on. So they pile up this way. But at the end, you just say, okay, these are all true as long as n is bigger than the biggest lower bound, and you can almost never do this. We have a few shortcuts that we use. We know how to do this, but it's almost never necessary. So we use some common shortcuts. So one of them is that the set n to the power c1, or order n, O of n to the power c1, is a subset of order n to the power c2, as long as c1 is smaller than c2. So for example, order n, right, that's n to the power 1 there, that's a subset of order n squared, which we think of informally as, yes, functions that grow like n, they don't grow as fast as those which grow like n squared. Plot them, these are the ones that grow like n, they look like a line, the ones that grow like n squared are these parabolas, and yet the parabolas always get bigger in the end. And then there's a couple of other common relations. If you have constants, any constants, a, b, and c, no, any one could be larger than the other, they just all have to be bigger than 0. Then order A, which we usually write as order 1, so that's a constant, that's a subset of order O log n, which is a subset of O of n to the b for any b, which is a subset of O of c of n for any c. These things are usually called, in this order, this is a constant function, this is a a logarithmic function, this is a polynomial function, and this is an exponential function. It's easy to compare this way. And now we make things, say, we can do things a lot faster. So for example, we want to compare 2 log n. Well, 2 log n plus 2 is order log n. So why is that? Because this tells us that the 2 here doesn't really matter, right? If I put, let's say, big O's around all these things, I have an O of log n and an O of 2, and this relation says that the O of 2 is contained in the O of log n. So it's implied by the O of log n. So the whole thing is bounded by O of log n, and 2 log n, of course, in O of log n, there's just a constant 2. N plus 2 is O of n. That's because here's the 2 is a constant. Here is O of n. So O of n is O of n to the power 1. So again, the O of n implies this. We get O of n. And 2n plus 15n to the 1/2 is O of n. Why is that? Which relation on that is being used there? Yeah. So the very first one says that n to the power c1 is a subset of n to the power c2 as long as c1 is less than c2. And what do we have here? We have n to the 1, and we have n to the 1/2. So 1/2 is smaller than 1, so the whole thing is in order n to the 1, which is order n. So these sorts of shortcuts usually are all we end up using. And sometimes you don't get something that fits into this pattern. The nice thing is you can multiply these things by any positive value and they still remain true. So, for example, let's multiply that whole string of inequalities here, inclusion by n, and you get that order an, which is order n, well, that's a subset of order n log n, right? That's what happens when we multiply this by n, which is a subset of O of n to the 1 plus b, for any b bigger than 0, which is a subset of O of n to the n times c to the n for any c bigger than 0, or c bigger than 1. C has to be bigger than 1. This c here is bigger. Luckily, in this course, we don't come across any exponential. Yeah. So, for example, if you want to know what's the relationship between n to the 1.5 and n to the 1.5 log n, just take the first 2 things and multiply them by n to the 1.5, and that tells you. Okay. Something else. We sometimes see expressions that look like order n minus I. That should worry you if you really know about big O notation. Because when there's only one variable, it's obvious what value this function takes on. What the arguments of this function are. In this case, we have a function with 2 arguments, n and I. And that actually can cause a problem. So we'll use a convention that the definition looks the same, but it's only for the values of I that make sense. So you're not allowed to call the add or remove operations in a list with a value I that's bigger than n, for example. Because that could make this thing negative, but that doesn't really make sense for the operation. So for example, in the list, the values of I that make sense might be 0 through n minus 1, or 0 through n. assignment, the first assignment you might get in a programming course as soon as you learn about for loops or arrays. And you want to just set the value, set some values in an array, I equals I. What's the running time of this code? Yeah. Oh, then. So that's a nice, easy, concise way to describe it. This loop, it executes n times, and each time takes constant time. If we don't have this big O notation, we end up saying, well, actually, no. The running time is the time it takes to do one assignment, setting I equals 0. Then we end up doing n plus 1 comparisons. That's I less than n. We also do n increment operations. Don't forget to do an array offset calculation. Then we do n indirect assignments where we assign a value to an array location. And so that says that actually the running time of this thing, if we didn't have big O notation, we'd have to write this as a plus b times n plus 1 plus cn plus dn plus en, where a, b, c, and t are the constants that depend on the machine that we're running. We would never get anywhere studying things. You can't get past the simplest for loop this way without introducing 5 different variables into the running time. But of course, we just say it's O n constant. Okay, so that's it for like that. Oh, yeah.
I gotta study for business. I gotta make sure it's not.
What do you do after It should only be like, it's only like an hour, right? What you guys do?
I'm going to do class next.
Like what you do during your
It's just like we learn how to use Minitab and find numbers. Like it's actually stupid.
4385. Okay, cool. I work on my resume after. It's one, so I'll probably go to the library. Is it still running?
You want to meet up in the library?
Mike, why did you skip class?
What's your laptop? Oh, the Fizz? For 1 and 2?
1, 2, 3. I did 2.
I looked at it. 1 was super easy. Have you ever seen such a laptop? Other ones we can. No, I tried.
Just takes some time. If you screw up one, your answer's going to be the thing that is screwing up. So he could say numbers. This T over 2. They cancel it.
Like I know I moved that sometimes they split it up.
Decided it's not, or not to reject it. Where is it? So close.
No, but it's funny. No. It was Melinda didn't show up to the first one. You guys let me know.
Yeah, this, I know where some tables are near mine.